Good evening, ladies and gentlemen. Here you are to witness another wonderful event brought to you by IEEE Plus Student Branch, University of Jaffna. This is the webinar on smart grid and renewable integration. First and foremost, I would like to welcome all the attendees to the session in this evening. It is my duty to introduce and welcome the guest speaker to today's session. Prof. Janaka Bandara Ekanayake is a renowned authority in power and energy systems, with a first-class honours in BSc Engineering degree and a PhD from Manchester Institute of Science and Technology. With 80 journal papers, co-authorship of 7 books, and a Google Scholar Edge index of 45, he is one of the Sri Lanka's most cited engineers. He has secured significant research grants totaling 2 million GBP in Sri Lanka and the UK, and has received prestigious awards such as CVCD Excellence Award, NSF Research Award for Scientific Excellence, and 7 presidential awards for research. As a Fellow of IEEE, IET, and IESL, his influence extends worldwide. Prof. Janaka currently serves as the Chair Professor of Electrical and Electronic Engineering at the University of Peradeniya, and holds visiting professorship at Cardiff University and University of Tenaga, Nationals, Malaysia. Prof. Janaka, over to you, sir.
Thank you very much, Yashidun. Can I share my slides, please? Yeah.
Yes, sure, sir.
Can everybody see the slides?
Yes, sir.
Oh, good. I'm going to turn on my video so that you will have a better view of my slides. Right. So I know that the topic is about smart grid, but I think it's better to look at why smart grid. So I slightly changed the topic to challenges and solution of future renewable rich grid. Now, in my talk presentation, I will be talking about what's meant by a sustainable energy future and barriers and solution for achieving such a future, which mainly supported by renewables, and where I will talk about the demand-supply mismatch, frequency regulation, stability, and voltage rise. Then I'll talk about non-technical barriers for renewable addition, system-level solutions for renewable addition, and considerations for renewable. Now, when it comes to the system-level solutions, that is where the smart grid really fits in. But we'll go through slowly up to that point. So this is what has been happening since the early industrialization. People start using water wheels to, produce energy. So many factories were running on water wheels, but then once the what you call the coal powered locomotives and vehicles introduced, there was a slight increase in the fossil fuel overtaking the hydropower. Then from 1950s to 2016, and so there's a huge increase in fossil power. That's mainly governed by the living style of the Western people, and also the rapid industrialization in China. With that rapid increase, you can see that the share of renewables has come down from 100% in 1850 to very low value in 2016. Now, then people realized that this is not going to work. It's going to create more issues for the world. So we wanted to change that pattern. So the every country is now looking at increasing their share of renewables and reducing the fossil fuel use. And also we wanted to make sure that the energy demand will be reduced or stopped. So for that, we need to have marked increase in energy efficiency. This is where the different technological improvements come, such as the heat pumps that are being introducing into this part of the world. Then you can use electric vehicles up to a certain extent. And with those heat pumps and electrical vehicles, the electrification of the heat and transport sector can be noticed. However, we need to achieve whatever the energy we wanted in the future using renewables, mainly solar, wind, and other renewable energy sources. So let me very quickly move on to two main renewable energy sources that are in operation. One is the wind. The wind, you can see how the wind turbines start changing. In 90s, we had a very small wind turbines where they were in kilowatt range and the diameters were around 50 meters. We had one similar in Mirichavilla in Hambantota, which was now removed. Those are called fixed speed induction generators. They are operating at a constant speed. They are squirrel cage induction machines. Then somewhere around 2000, the double-fed induction generators start coming into the field. And that's a wound rotor induction machine with a back-to-back converter feeding power into the rotor. But they didn't last too long. Soon they were replaced by the full power converter inverters, wind turbines. They are in the range of 3.5 to 6 megawatt, and you can also see the increase in the rotor diameter. But today, this gearbox, which was used in early design, has been replaced by a multi-pole synchronized machines. These machines has around 100 poles, and there comes in big sizes. Like for offshore applications, you can get wind turbines having up to 15 megawatt. The rotor diameter is 200 megawatt, and you can compare the size of that wind turbine with the largest the flight that is available in the world. So you can see how big they are. Similar development has been seen in solar. Of course, the solar market is still dominated by crystalline silicon. That is the first one. The crystalline silicon has a market capture of around 80%. Of course, we have gallium arsenide and triple junction, multi-junction devices also available. These are called wafer-based technologies. There are limited amount of thin films technologies available, but they are still, very small numbers. Sorry, I'm just trying to get some water. The commercial thin films are amorphous silicon. As you know, most of the windows have amorphous silicon films. Then you have cadmium telluride, copper, indium, gallium sulfate or something, and copper, zinc, tin, and something. So these are the variations that are available in the market. There's another new thin film version coming into the market. This is a new substance found in Russia, perovskite or whatever the way they call it. And also we have in very limited quantities organic diselenides and quantum dots. If you look at the multi-junction PV cell, main difference is it uses 3 types of material to absorb energy from different spectrums of our solar. Now, the silicon can take from wavelength from 200 to somewhere around 1100. But there are a lot of energy beyond that. So what is done here, you use a prism on the top and you break the sunlight into different layers. And the first layer go to gallium indium phosphate layer. The second layer will go to gallium arsenide layer. And the final will go to a germanium layer. By doing that, they have achieved a very high efficiency. Now, when you look at the efficiencies, what is seen in the purple line is the multi-junction ones. You can see the laboratory. These are not commercial efficiencies. These are the laboratory efficiencies. The laboratory efficiencies of them has reached 47%. The silicon, which is the blue ones, they are in 20s. And you can see this one with the yellow dot. That is the perovskite. For silicon to reach that efficiency, it took so many decades. But the perovskite came into the market very quickly. They're still having some issues, but that's a very promising technology which is coming up. And the price, that's the most important thing. The price has been going down drastically. For a residential level PV, the price is somewhere around $2.71 per watt. And for utility scale PV, the price is somewhere around $1 per watt. So you can see that price has very quickly come down. Now, other thing we have noticed is during the COVID period, because the demand suppressed in many countries, we have seen many countries are operating with high share of renewables. For example, Denmark operated where the variable, this is VRE, stand for variable renewable energy, which is solar and wind, exceed the demand for 845 hours, which is roughly 1/10 of the year. The extreme case was the generation was 3,600, whereas the demand was nearly 1,000. So you can see that more than 3 times generation were available from VREs. South Australia, 77% of PV generation was from distributed PV. So they have been contributing tremendously to their output. And Tasmania, which is just the island below Australia, they again has 90% of non-synchronized generators, which are solar and wind. And Northern Ireland and the Ireland in January 2021, 90% of 5% of the demand met by renewable. This shows that there is a room for anybody to go into that sustainable future. Now, we are also heading towards that. This is what Prime Minister of India said. The sun has a great potential, so we must run the world on sun. They are putting a lot of effort. Whereas us also putting a lot of effort to expand our solar PV capacity. Sorry, for example, right now maybe around 700 megawatt or 750 megawatt. What we want is by 2030 around 4,700 megawatt, and 2042 around 10,000 megawatt. This is what the long-term generation expansion plan of CB tells us. So there are I mean, I can't see huge the programs to achieve that, but there are, the lot of new additions coming in. Yeah, I'm sure you can see some of them coming in your area. Okay, let's look at what are the barriers and solutions for achieving the renewable energy targets, mainly looking at the demand and supply mismatch. Now, looking at the barriers, now what you are seeing here is minimum net demand days in different years in Australia. Now, what is mean by minimum net demand days? As I showed you before, they have a lot of rooftop energy, rooftop solar. So the house demand at somewhere around 12 noon will be their utilization minus solar output. As you know that many houses, nobody stayed in the daytime. So the energy or the power they will absorb from the grid could be even zero. So if you add the entire South Australian network together, in around 2006, that they had a daytime demand of 9,953 megawatt, but with the introduction of solar PV, they came down to 598 in 2013 and came down to even 62 megawatt in 2009. Now the issue here is because the solar PV generated locally at the house, the grid operator doesn't know what's going on. So they can't see how much is generated within the house and how much they will ask from the grid. At the same time, you may be here, suddenly a cloud comes on top of the large solar farm and it goes up. So for the grid operator, it's a bit of a nuisance to making sure that the system is stably operating under this kind of scenario. The other issue is, running a system at that kind of net demand, you need to get to switch off some of the plant. Of course, you can easily switch off, hydropower plant or single cycle power plant, but, switching off a coal power plant is a nightmare. So you can't switch off. What is happening is you kind of reduce their load to zero. So they are still running, still spinning, but not producing any power. So you can see that in UK, they have to do it every day. This is called the daily cycling. But there was a particular day, that was the 21st of April 2017, they have to spin their coal power plant for more than 24 hours because there were too much solar on the system and the wind. So this is a big issue because you are, spinning a large machine is money, but it doesn't produce any electricity, so there's no revenue. So it's a big issue for the generator operator and big issue for the network operator. This is another example from Japan. On this particular day, they had a solar PV generation of 5.5 gigawatt. So they reduced their thermal power generation to the minimum possible. So you can see that is from 4.8 gigawatt to 2 gigawatt. These are called the base load power plant. Usually you run them at the constant value. So there's no, this red line is the demand. The red line is the demand. You take a pointer. Here's the point. Yeah. This red line is the demand. So you can see that somewhere around 12 noon, you have met all the demand by baseload power plants, the very limited amount of fossil fuel power plant or thermal power plant and solar. Of course, they are lucky they have pump storage, hydro, and batteries, so that can absorb quite a lot of power available. But still, some of the renewable energy sources were asked to curtail or stop. So they lost around 1 gigawatt there. So all this power which was stored is used in the night to manage the night peak. So what this suggests is, if we wanted to run a system with large penetration of renewables, you will need a large energy storage. Now, in Sri Lanka, we have very limited energy, not a single pump storage hydropower plant available. CB has been, doing feasibility studies from the day I know, but nothing has come out yet. Very limited amount of batteries are available, so you cannot easily run a system like that. Now, other issue is the issue of predicting the solar or wind. Now, you can, roughly forecast wind. You can see the actual wind speed in blue. What you can predict is the average wind in green. However, what you really forecast is this red one. You can't actually, there is always an error. So in order to compensate for that error, we have to maintain what we call the regulation. There's one regulation to come up, to support that variation, and there's another regulation to supply that change. So you can see that if you wanted to minimize these two regulations, these are what I mean by regulation is other power plants such as single cycle diesel power plant or hydropower plant can do that. Just spinning with lot of extra capacity so that they can change their output where your requirements are. So like even if you do it pretty real time, there is an error, forecasting error. That's what you are showing here. But if you try to do it like, right now, Sri Lanka, we have day ahead scheduling of power plants. In that case, your solar power plant's error, wind power plant error could be as high as 12%. That means our 100 megawatt Mana wind farm, you may predict it as 100 megawatt, but what you are producing actually could be only 88 megawatt. So you can see that 12 megawatt has to come from somewhere. That is what we call the regulation. Now, this is, of course, you can get rid of all these issues if you have energy storage. So the solution for treating the variability and intermittency of renewable energy power plant is the energy storage. Here I am showing you a wind farm in Japan, a Rikoshi wind farm, which has a total capacity of 51 megawatt, which is also supplied with the 34 megawatt of sodium sulfur batteries, which is 2/3 of its capacity. If you have that large amount of batteries, you can do anything. What you are seeing here, the yellow one is the wind farm power output. This line, the constant lines are what the utility wants from this wind farm. This is called the scheduled amount. Now, during this period, the scheduled amount is, the wind output is greater than the scheduled amount. So you can charge your battery using the excess energy. During their period here, the scheduled value is much higher than the wind output. In that case, you discharge the battery. By doing that, your actual output, which is given by this process, can perfectly match what the grid wants. But in order to do that, you need large energy storage, as I just showed you. The other issue is, as we all know, we wanted to maintain the system frequency at around 50 hertz. So you have a plus or minus 1% margin for your frequency. But with such a variation of power output of wind and solar, regulating the frequency at that value is a nightmare. More importantly, if there is a event such as large generation tripping from the network or large load connected to the network, you are going to see a dip in the frequency. So what you are seeing here, the red one is at point A, you lost a generator, the frequency goes down and it is stabilized by the governors of large generators and bring it back to a value, not the 50 hertz, but slightly lower value, and later you can rectify that. That is what normally happens. Now, during this phase, all the synchronized machines that are on the system provide what we call the inertia response. The synchronized machine will start slowing down because we know that the speed of a synchronized machine is proportional to the speed of frequency. So when the frequency is at 50, it has certain kinetic energy. When its speed comes down, it starts releasing that kinetic energy. That is what we call the inertia response. So the inertia response is the one, and also some large motors produce what we call the load response. Those two and the governor response will try to stabilize the frequency and bring it back. Otherwise, it will start going and the system will collapse. Now, that kind of inertia response is not there in wind turbines, not there in solar plants, because of the power electronic interface involved. This is an example from UK. On this particular day, 27 May 2008, they lost around 300, the large generator of 345 megawatt at around 11:34. And due to an unconnected reason, and second generator lost at a few minutes later, they're not connected to each other. That was again 1200 megawatt. So the frequency was going down, as you can see, very rapidly. Frequency was going down very rapidly. Now, what happened was, with that frequency, these small wind farms has under frequency relays. They start operating and removing the wind farm. So they remove around 40 megawatt of wind and 120 megawatt other small generators. Now, loss of that is reducing the frequency more. So frequency starts stabilizing, but it couldn't, and it started going down by losing some more embedded generators, small generators, and you can see that frequency has come to a very low value. Now, the good thing in the UK, there is a very large pump storage hydro scheme available in the UK called Tenaga, which is not far from where I am sitting right now. dinner which is can come from its motoring mode. Remember this, what is meant by a pump storage plant is, if you don't know, you have a reservoir up there, reservoir down here, and you also have a motor generator set. During the time where this reservoir is full, you take the water through that penstock, rotate the generator, produce electricity. So, and when that reservoir come down to a certain minimum level, you stop producing electricity and you pump water from the lower reservoir to the upper one. So that works as a motor. Then you know that any electrical machine can work as a motor or a generator. So this particular time, the Dinovich was in pumping mode. So it quickly changed from pumping mode to the generating mode. So it starts producing twice as much as power that it can produce. The Dinovich can do that within around 10 seconds. It's around 12 gigawatt, very big plant, and it can go from pumping to generation very quickly and recovering the system frequency back to 50 Hertz. So if you have pump hydros of that nature, yes, you can do things, but not without good storage. Okay, I'm going to skip that slide. Now here again, you can see the frequency response provided by small solar. As the frequency goes above 50 hertz, the solar power output has come down. So 30 to 100 kilowatt 90 watts sites has reduced their power output. If the frequency comes down below the 50 hertz, they are increase the power output. This is a real graph obtained in South Australia. In South Australia, of course, they are introducing these large Tesla batteries, and they can do any wonders. So like here you can see the frequency has come down, the Tesla batteries has provide additional power to bring the frequency back. When the frequency goes down, it can absorb that and somehow stabilize the frequency. So if you have energy storage or pump hydros, you can manage that kind of system. The stability wide, I'm showing you two blackouts. One is in South Australia again, where a lot of wind turbines were tripped. You can see that this is the total wind power output. It has reduced from 900 to 700 at one point, and from there again to 400 and finally collapsed. This is because there were lightning strike, repetitive lightning strike on the system. So that has created a blackout in South Australia. So these are unexpected, though it's very difficult to figure out why it has happened. Very similar one, the London blackout in 9th August. It was London. London is down here. But the blackout has happened due to an issue in a wind farm far away from London. There was instability, we call the subsynchronized instability, and that has created this. So this, you can manage these normal issues, the frequency regulation, the demand supply mismatch, but the stability issues are beyond one's control. If they happen, it's very difficult to rectify. So one thing you can do is you can generate a very detailed model of your power system the UK has extremely detailed model where they can study various scenarios. So you can do possible scenarios offline and take actions for those scenarios. I mean, there are now what they call these wide area monitoring, control, and protection schemes that can take actions. You run them offline and store them in a computer, and they can automatically come in if there is any action of similar nature. Other local network has having real issue of voltage rise. What I'm showing you is a feeder in Australia. Sorry, feeder in Germany. Early morning, the voltage at that the feeder is 1.02, beginning of the feeder, and the people or the consumers were absorbing electric power of around 1,500 kilowatt. As the day goes, rooftop solar start producing electricity. So you can see that the power absorbed from the grid goes to zero somewhere around 9:30. So there's no more power absorbed from the grid. With that, the voltage will slowly start rising. Then, after that point, there are more excess generation than the demand of houses. So the reverse power flow start. That means from houses to the grid. And you can see when the reverse power flow started, voltage starts rising. In between, you can see these peaks. They are due to cloud cover. If cloud comes, power drops to lower value and you are absorbed from the grid again and so on. So that will reflect on the voltage also. So this is problem. In Europe, if that voltage goes above 1.1 per unit, that is statutory or legally not allowed. Same thing was experienced in South Australia. You can see that there were the upper limit is that there were so many sites above the upper limit creating voltage rises. Now, one thing you could do, this is kind of now slowly coming into what we call the smart grid approaches. Your your solar inverters can be asked to supply reactive power to the grid. By doing that, or supply you absorb reactive, you can either supply reactive power or absorb reactive power. So these solar inverters will obviously send active power that way, but they can absorb or generate reactive power to the grid. If the voltage goes up, you absorb reactive power and reduce the voltage. So this is called a STATCOM operation, static compensator. By changing the voltage of that inverter, you can either absorb or generate reactive power. Now it has been made mandatory in the latest grid codes or the connection codes. In US, they use IEEE 1457, 2018. UK, they use G99 and G95. In Sri Lanka, our grid code or the connection code for distributed generating is very old. So, we don't have this kind of mandatory reactive power support requirement, but it's now been mandated in other countries. So coming into the bigger picture, you can run optimum power flow algorithms and schedule the solar farms to provide the reactive power requirement to obtain the voltage regulation I am talking about. I will skip this for the time being. So what we can do in the system level? The system level, you can already we have what we call the network layer, which is the transformers, the substations, line. We can add our electronics layer. On top of that, we can add renewable energy and storage. Then we can have a lot of sensors, big IoT network, smart meters, phasor measurement unit, and so on and so forth. And then we can connect them using an ICT layer. There are ICT protocols for substation, IEC 61850. For houses, we have PLC, Wi-Fi, WiMAX, and so on. And then we can do what we call the distribution automation, so that your lines can automatically be connected or disconnected depending on the faulty or line loading conditions. And all that can be integrated into what we call a modern control center. When you have such a system with so many layers, we call it a smart grid. So you can consider this as simply, if you look at our body, our brain is more like our control center. The brain sends signals through the nerves to muscles, and muscle is our power electronics. So that part has been replacing the intelligence, communication, and automatic actions on top of the existing network layer. So that is basically what we call the smart. But the smart grid doesn't have a single definition. European technical platform defines the smart grid as a smart grid is an electrical network that can intelligently integrate the actions of all users connected to it, generators, consumers, and those that do both. Like now, of course, you have people who generate and consume. They are called prosumers. In order to efficiently deliver sustainable, economic, and secure electricity supply. The US Department of Energy defined it as a smart grid uses digital technology to improve reliability, security, and efficiency, both economic and energy, of the electric system, from large generation through the delivery system to electricity consumers, and a growing number of distributed generation and storage resources. And UK, according to Department of Energy and Climate Change, the smart grid uses sensing, embedded processing, and digital communication to enable the electricity grid to be observable, so that you can go and see what's happening inside the house through a smart meter. Controllable, you can manipulate anything in the house. Automated, fully integrated, and with the capacity to incorporate diverse set of energy. So you can see that there's nothing called single definition for the smart grid. It's all changing from country to country. In Sri Lanka, we don't have a kind of definition. We had a group looking at the roadmap to smart grid, but nothing has come out. So in nutshell, smart grid enable real-time visualization of the power system, support enhancement of power system security, relieve system bottlenecks, enable self-healing, and enable connectivity to consumers. This is a very simple example of smart grid. I'm sure you have learned that the power equation, which is V1, V2 over X sine delta, but you can manipulate any of these now. You can change the voltages by static compensators, reactance by a series capacitor or a thyristor control series capacitor, angles by a phase shift and transformer, and on top of that, you can also add a DC line, which is independent of this equation. For example, this is an example in US. from Petersburg to San Francisco. This was the congestion of the network before putting up this new line, which is, you can see from red. That's a DC line on parallel to all the AC lines available. So they have a very congested network. So they were looking at a connection between these two and finally found a connection through the Great Lakes. And once you connect that HVDC link, high voltage DC link, between these 2 points, you can see the congestion has severely reduced. This is one of the early new design of high voltage DC, which has a capacity of 400 megawatt operating at plus or minus 200 kV. You now have smart meters sending data to a data concentrator. There are so many data concentrators in a region, and all that goes to what you call a central controller. Then the central controller sends messages back all the way to houses. The infrastructure is there in Negombo and Katunayake. There are thousands smart meters which has a very similar. So there are a lot of concentrators in different areas. They are connected to local control centers. One belongs to CB and one belongs to LECO. And that is then connected to a larger control center, which was at BMICH. I don't know where it is now. So which is there, but of course there we are not doing anything. This just it's a pet which we created. And you can now see a huge ICT infrastructure on our networks. Different components are connected. And you can also introduce distributed generation. That today there are devices. I will show you the device first. These are the devices. They are pole mounted. So the pole mounted devices with a controller underneath. What you could do is you can open and close certain section of your distribution line using these devices. It's a very clever device. I know that north of UK, the Scotland area, they have installed thousands of these devices. They allow what we call agent-based control, which I'm not going to go into much detail due to time constraints. But basically, if there's a fault, these agents will talk to each other, and from these devices that I showed you, you can disconnect these two and still supply power to all the consumers except, of course, L4. But right now, like if Sri Lanka, if there's a fault here, somebody has to phone CB, otherwise CB doesn't know that there is a fault. Once somebody phones CB, they will wait for a few more calls, and then they will send somebody to come and repair it. Until such time, everybody on the line, everybody on that line will not have electricity. So so it's a quite. But if you have this arrangement, within 5 seconds, L1, L2, L3, L5, and will get electricity. Only L4 will have little time to receive the electrical supply. Again, I'm going to skip that. This is another concept which has been trialed in South Australia, which is called a virtual power plant. When we have the ICT infrastructure, you can have a very small power plant, but you can have an aggregator who will aggregate these small power plants and make money. It's a little like you can go, look at Uber. The Uber is not a big train, which has thousands of drivers, in different places, and they are connected through an ICT layer to some Uber headquarters, and they manage the the transportation in a wide net area. Each house they have the Tesla batteries or Samsung batteries and solar, and they all have the ICT connections. So if the frequency of the country goes down like that, collectively they can provide. This is from site one. This is the total VPP. So the one house will only provide kilowatts, but the entire houses that are on that virtual power plant can produce megawatts. So, in conclusion, even though there are issues for renewable addition in all voltage level in power system, there are possible solutions to mitigate them. The selection and adaptation of mitigation actions mainly depend on economies and policies in place. Obviously, what's going to happen is there's what we call the energy trilemma. Everybody wanted to decarbonize their networks. In order to decarbonize, we add more renewables. So we are coming, our system is coming closer to zero carbon. But we also need to maintain certain amount of reliability, but reliability will slightly increase when you add more and more renewables. Obviously, the limiting factor will be the affordability. Can people afford it? So that's the final limiting case. So I will stop there for leaving few minutes for people to ask questions if there are any. So let me unshare my document and turn on the camera so that people can ask any question.
Is I'm not clear about this virtual power plant concept. Could you please elaborate it more?
It's as I told you, like if say that you have a solar plant, which is say 2 kilowatt, and can you do something to the grid? Can you change anything in the grid with that 2 kilowatt?
No.
No. But you form the community around your house. 100 of your people who owns solar plants get together and form a network, and that network now has say 1 megawatt. Now you have more influence. This is like the Uber is trying to influence the transport network. So the virtual power plant is like that. You are not going as a single person. You are connected through a aggregator, we call it, and you are connected to the aggregator through the ICT link, and collectively aggregator get 50 megawatt and then go and tell the grid, look, I have 50 megawatt, can I connect to the grid and give you certain services? Now in Sri Lanka, we don't pay for these services. In Sri Lanka right now, we are only paying for energy. But this part of the world, they have more services than energy. Because when you have more renewables, the energy is not our barrier. Capacity is one of the barriers. Now, large generators have a capacity charges, but not these small guys. So if you wanted to get a capacity charge, you can go as an aggregator, as a virtual power plant. Will it explain a little bit?
Yes, Professor. Thank you very much.
Yeah, sir. I'm Akila, and good to see that you are presenting to Jaffna University graduates. And I have one question. Maybe what is your opinion, or maybe can you give some insight about the wave energy converters, like as a renewable energy source? What is the current status?
Yeah. The main problem with Akila, good to hear your voice. Main problem with wave energy. it has not converged to a single business design. Now, when you look at cars, all cars has 4 wheels. All cars looks pretty similar. I mean, there are slight aesthetic differences, but they look similar. Same with wind turbine, 3-bladed wind turbine. So you get a set of manufacturers who produce parts for these things. Whereas when you look at the wave power, there are, if you look at the literature, you will find at least 100 different variants of wave power. That indicates that it has not reached the kind of commercial level. When it comes to the commercial level, you will find one manufacturer producing hundreds of them. But that is not the case with wave power. And they, with these harsh sea conditions, it's not really, picking up. But there's good, what you call the advancement of tidal power, which is the small wind turbines. Keep it under the sea. Remember, the density of air is 1.2 to 5 kilograms per meters cube, whereas density inside the sea could be 35 or something kilometer. I can't remember the exact numbers, but very large number, say 30 kilograms per meter cube. So it is more than 10 times the density of air. So these tidal streams, when they are producing energy, the size of the tidal stream turbine that required to produce the same amount of electricity as from a wind turbine, maybe 1/10 of the size. So they are very small in size. Because of that, the tidal energy is picking up, but wave energy is more, still you have a lot of demonstration versions. The hopes are very limited.
Yeah, thank you, sir. One more question. I'm not taking time, but since we know that if we are talking about tidal or wave energy, it also will be dynamic, like solar or wind. So in that case, what are the energy storage systems? So what are the systems that can use for the dynamic changes?
It's same. It's batteries. I mean, obviously it's batteries. Because when you come to, if you have a pump hydro station, which is, of course, pump storage hydro is more system level. But if you wanted your plant level, it has to be batteries. There's no other alternative, but batteries are still expensive. That's why batteries are not picking up quickly.
Yeah, okay, so thank you. Thank you very much.
Excuse me, sir. Another question.
Yeah.
Sir, in your slide, you say...
Just 1 minute. You can see.
In your slide, you mentioned the hydropower plant. There was a peak time it's generated the voltage, and off-peak time it's work as a generator and bring the water in the upper reservoir. Like that, can't we use that technology in our Sri Lanka system in this situation? It is applicable to use this situation?
Yeah, but you need to convert right now we don't have these are called pump storage hydros. We don't have a single pump storage hydro, in the country, or, none of our hydropower plants were designed for that purpose. Now, of course, there's one in the pipeline. I can't remember the exact location. Maybe Professor Putaraja may be able to remember. Somewhere in Kegol, my memory. That is the very first pump hydro which is going to come in the country. But
So is there any other questions or doubts that you have to clarify? We can give you 1 minute time, and feel free to unmute yourself or put your messages or comments
and also your doubts and questions in the chat. And we'll let you a time of 1 minute more. We got another question, sir.
There's one more question.
Yeah.
How about the preparedness of the distributed network in UK to absorb DERs? Any particular design or planning highlight to share? There are quite a lot, but probably we don't have that kind of time. They are here, the DERs came into the picture long time ago. It's not new. If you look at our book on distributed generation, which was published in 2000 or somewhere, that time you could find DERs coming up. So it's not something new in the UK. So there are quite a lot of arrangements are there.
So, ladies and gentlemen, with that, we shall mark the end of the questions and answer session. So now I think it's my duty as a member present in IEEE PES that to show our gratitude to Professor Janaka Ekanayake for being here with us and nutrifying with us with his tremendous expertise and knowledge. Ladies and gentlemen, here we present the token of appreciation to Professor Janaka Ekanayake. Thank you, sir, for being our guest.
Thank you very much. Thank you very much.
In Smart Grid and Renewable Integration webinar, which happened today. And also, I want to mention that we have put the feedback form in the chat. You can give your feedbacks to us. And also, we have also added the virtual background that you can use. And now we have come to the end of the session.
Thank you, everybody. Bye for now.
Thank you so much.
Welcome.
So now, and here we are marking the end of this webinar. Ladies and gentlemen, be with us. And we will organize these kind of very extravagant, important events, which will nutrify you with the best expertise in the power and energy and integration. So be with us. This is IEEE PES Student Branch Chapter of University of Jaffna. Signing off, Akita Anupriya.
Thank you.